This is a summary and explanation of the paper Formation, Stratification, and Mixing of the Cores of Earth and Venus by Seth Jacobson and David Ruby. This paper relies on observational evidence of Earth's global magnetic field, a density profile matching that of a compressed homogeneous liquid, and Venus's lack of a magnetic field. Earth's magnetic field is created by a geodynamo, a self-sustaining layer of convecting conductive liquids. For this dynamo to exist, the core must have a sufficiently large convective zone, which is created by adding mixing energy through massive collisions. In short, we want to take a poorly mixed core, as shown on the left, and find out the steps required to make a core similar to the one observed on Earth, which is shown on the right. This work will help constrain the timing and size of the Theia moon-forming collision, and will explain the origin of Earth's magnetic field, which provides a protective layer for our atmosphere against the solar wind. We'll see that without some late massive collision, life on Earth would likely not be possible. In the most basic sense, we're going to build up a terrestrial planet that is similar to Earth and Venus, and then take large objects and just ram things into them and look at what the core looks like during all these different stages. First, the authors run a simulation of oligarchic growth to produce an Earth and Venus-like planet. Oligarchic growth follows runaway growth when the mass within the hill radius is depleted and consists of a few larger moon to half-moon-sized objects accreting meter to kilometer-sized objects, with occasional collisions between the more massive objects. The parameters chosen in this model are based on previous work by this group and produce the desired planets while also recording a late, massive collision with the Earth-like object. The model used by the authors will follow the bottom half of this diagram. We'll begin with a bunch of small, undifferentiated bodies that will then grow their own cores and accrete onto the more massive objects. The cores will then differentiate and form a single core that is shown at the end of this diagram. Differentiation is the sinking of more dense core-forming material through the mantle and results in heating of the core through adiabatic compression and loss of gravitational potential energy. The authors considered two cases. One, shown in the top figure, where all of the thermal energy due to gravitational potential energy loss is retained. The second figure corresponds to the loss of this thermal energy through conduction with the mantle. Notice that the figures display the exact same density profile, showing that this thermal state of the core has negligible effects on the density profile. The authors will use the case where all of the gravitational potential energy is converted to thermal energy and lost in order to allow heat transfer between the core and mantle. The plots to the right show that the abundance by weight of the light elements oxygen and silicon increase with increasing planet mass. This is due to increasing equilibration temperature and pressure. Equilibration temperature is the temperature at which half of the addition melts. Without melting, light elements cannot leave the accreted mass and contribute to a lower density profile. When mass is added to the planet, the thermal energy and pressure increase. When the pressure increases, higher temperature is needed to melt the accreting mass, similar to how it takes a higher temperature to boil water at higher pressures. This causes the density of core additions to decrease with time, as shown by the horizontal branches in the density profile. Note that the composition of a core addition is also determined by where it originated from, so more dense additions may be deposited on less dense additions, resulting in an unstable density profile. On the right side of the plot, where we see the total light element abundances, we can see a region where the core is unstable due to its density profile. I'm circling a region of high density, and notice that it is above a region of low density. This is unstable, and the core must mix or swap in order to correct the density and place the lower density material on top. The core has two strategies for resolving density instabilities. Swapping corresponds to laminar flow when the particles move in the same direction as the bulk motion of the fluid. Mixing corresponds to turbulent flow when the particles have velocities separate of the bulk motion of the fluid. The diagram shows mixing with a higher density layer deposited on top of a lower density layer. They combine into one layer of intermediate density. Mixing will continue until you have a core that looks like a compressed homogenized liquid. This diagram shows swapping of two layers. Whenever these two layers swap, they simply exchange densities. Adjacent layers will continue to swap until you have a stable core stratification with lower density layers on top and higher density layers on bottom. These two plots show the density profile after mixing or swapping has been enforced. You'll notice that the density profile for swapping retains more structure, as shown by the greater distance between the black curve and the dashed line. Notice that neither remove all of the core instabilities and that further mixing would be required to remove all of this structure. Convection forces the core to mix further and helps the density profile more closely match the profile of a compressed homogeneous liquid shown by the dashed line. After convection happens, there are still horizontal branches in the density profile that correspond to areas where the density gradient deviation is negative. Density and temperature differences drive convection by applying a buoyant force on core liquids. Regions where the density deviation gradient is negative are regions where the difference in density between adjacent layers is small, so small in fact that they do not provide a sufficient buoyant force to mix these regions through convection. These layers are impermeable to convection and prevent the core convection from establishing a geodynamo. This profile is how we would expect Venus's core to look and suggests more mixing energy must be applied to the core to create the Earth's magnetic field. So if convection doesn't provide enough energy, we must receive some from a more massive collision, just like the Theia impact. To determine the size of the impact, the authors calculate the required mixing energy as the difference in gravitational potential energies of the density profile shown in the previous slide in a fully mixed core. They then calculate a mixing efficiency by assuming half of the collisional energy is kinetic energy imparted on the body, a third of that energy ends up in the core since the core is a third of the mass, and a fourth of that energy is used for turbulent mixing. This is the main source of uncertainty in the models, and laboratory experiments need to determine mixing efficiencies so that these models may be used for future work constraining the mass of the Theia impact. This should not cast any doubt on the results, however, since we have still shown that a geodynamo cannot result from convection without some more turbulent mixing occurring in the core. The two figures show the results of a low mixing efficiency and high mixing efficiency following the same impact. You'll notice that the right-hand figure shows that the density now matches that of a compressed homogeneous liquid, while the left-hand figure does not. It is also interesting to note that the density profile on the left-hand side could be that of an object that underwent an early massive collision and then later had collisions that were not massive enough to cause turbulent mixing, and so it still has some stratigraphy on the top of its core. I find the results of this paper highly believable, partially because they're trying to solve an inverse problem. We've observed the stratigraphy of the core and know that there is not a whole lot of structure outside of that of a compressed homogenized liquid. The paper was successfully able to recreate a core with such a structure. We should also not be concerned about the lack of information on the mixing efficiency, since it does not impede our interpretation of the results. Ultimately, we showed that a massive collision must happen for the core structure to be such that we have one large convecting cell creating a geodynamo that creates the magnetic field. Whether or not this happened in multiple somewhat large collisions or a single large collision does not matter. It only matters that the collision occur late in the formation history so that no future accretion events can deposit more impermeable layers. For future work, determining the mixing efficiency of massive collisions will help constrain the mass of the Theia impact. While there will still be uncertainties in the velocities and angle of impact, this can provide a lower limit on the mass. In addition, we need to determine better constraints on the protoplanetary disk from which the solar system formed. The authors had to force the composition of the mantle in this scenario to match that of the Earth. This doesn't affect the results since the composition only determines the amount of energy transported between the core and mantle, and we know the thermal structure has negligible effect on the density profile. Constraining the disk composition could help us understand where the cores of planets formed, which will in turn shed light on planet migration. It would also be interesting to model the magnetic fields of planets with different core structures. The authors touched on this briefly. However, I was curious if a sufficiently large early impact could result in multiple large convecting layers that produces a magnetic field with more than two poles.